This lecture is going to be on how, what, and why we see. Here we're going to look at the human eye. We're going to look at the process of seeing. So it's important that we pay attention to the components of what goes into it. There's a couple different aspects that we'll want to view, and we'll look at this in detail. But essentially I'm looking at this eye here, and I've got light coming in. Remember, light can be, photons that are entering the eye, and they can have they can be from an object that is emitting light, right, like a light bulb or a star, or it can be reflected off of something, and that's where the additive and the subtractive color processes come in. But let's just say light is entering into the eye, and we'll talk about the pupil, which then refracts then through the lens, which then lands on the retina, which is divided into particular cells that divide it up into cones for color and rods for intensity. And this gets transmitted into the optic nerve, which then signals it to the brain, where you make your decisions and kind of how you process your world. So if we take a look here at this little picture here, it's figure 22.8. The human eye has a couple different types of photoreceptors, cones and rods. And it's important that we realize that cones respond to color, right? The letter C should help you kind of make sense of cones and color. And rods, well, they respond to intensity of light. The pupil is what's dilating and contracting. It's really based on how much light is available. Where at night you would have your eyes that would be dilated. They'd want to make sure that they're opened up to be able to take in as much light as possible. Where in daylight, well, let's just say they'll be contracted. Here we've got the lens. The lens is what is refracting light, and the refraction of light is transferring that light energy that's coming in. It's putting into one particular location onto the retina for you to be able to make sense of that light. And this is where it then gets subdivided into the cells, or the cellular activity of the cone cells, right? The natural cone cells that the human eye has are red, green, and blue, right? Which is only fitting that they are the primary colors in the additive process, right, of making sense of light. So it makes sense that the cones would be red, green, and blue. And then rods involve the intensity of light. And there's a tremendously larger number of rods of intensity than there are cones. That's important because if too much light can damage your eye, and your body is always trying to protect itself from not being injured or damaged. And then you've got the optic nerve. This is what's communicating the information. This is signaled to the brain, and this allows you to then make changes into what it is you're doing. Too bright a light, you blink, or you close your eyes, or you respond behaviorally. So now let's talk additive process, and it's important we realize that the primary colors are red, green, and blue, which are the same cones that represent or found within the eye, right? These are your primary colors. Your secondary colors are simply mixtures, red and green mixed to make yellow, right? We're talking light here. Green and blue mixed to create cyan, and red and blue mixed to make magenta. And if I mix a complementary color, that's a primary and a secondary, they equal white. So red's complement is cyan, green's complement is magenta, and blue's complement is yellow. Any of these combinations are essentially mixing red, green, and blue to get white light. When I look at the color signals as to why I see green in the case of a leaf here, well, let's just say that the leaf itself, we can start talking about, well, what's it doing? It's reflecting green light. Therefore, it's absorbing red and blue. And as a result of this, we're getting light, these cones that are, let's just say, signaling to the green cones within our eyes that say, hey, you know what, it's green. And orange here, a strong signal from the red cones and a weaker signal from the green cones tell the brain that the fruit is orange. I kind of find it interesting here is that if you look at mixing red and green, we would get yellow. But really, if I add more red to it, if I enhance the red effect on yellow, I get orange. So orange is the result of more red than green, and blue would be clearly absorbed by this particular fruit. And last but not least, the subtractive process. It's essentially saying that if white light coming from the sun hits cyan, cyan is going to subtract or absorb red, and it's going to then reflect green and blue to our eyes, and therefore the mixture of green and blue light, we view this as cyan. So the pigments are going to be absorbing, and that absorption process is like the subtracting. It's subtracting from white light. Here we have white light, once again, red, green, and blue, and yellow is going to subtract or absorb blue, and therefore red and green make it to our eye. So we view this as a light combination of red and green, which we view this color as yellow. And last but not least, the mixture of cyan and yellow subtracts both red and blue, so only green from the light remains. So if I mix cyan and yellow, I would then get green. Another way of looking at this is if white light is shining onto green, it's going to absorb the red and the blue, and green is going to reflect to my eye. So this is a couple different ways in which we can view how white light is interacting with pigments. The subtraction process is literally, we're taking white light, RGB, and some of that light is being absorbed, which is what we call subtracting. If I add cyan plus yellow, I see it as green.